finding equivalent resistances. Okay, so resistors in series. Series means one right after another. So I've got some current flowing. Any current that flows through that resistor, let's call him R1, must also flow through this next resistor. There are no junctions in there. Any current, so I've got some current flowing that goes through one, must also go through resistor 2. Then we could, if we wanted to, pretend this is just one single resistor that we call the equivalent resistance or equivalent resistor. We could squish these together by just adding them. The equivalent resistance is just the sum of all of our resistors. Say we had n of them, I equals 1 to n. Resistors in series, just add together. Resistors in parallel, add as reciprocals. So I've got some junction here. I've got some current flowing. And that current is going to split up. Some of it's going to go through one resistor, some will go through the other. I could pretend, squish these together, that this is really just one resistor. And that equivalent resistance will follow this equation. The equivalent resistance is the sum of the reciprocal of the equivalent. If we had n resistors, would be the sum of the reciprocals. Okay, so let's do some examples. Now, when we're solving circuits, this is not your first go-to. Like later on the test, on that group assignment that I'm currently working on, and I'll post it later today, I would not try to combine the circuits together. Kirchhoff's rules are like a shortcut. I would not, on this assignment here, try to do any kind of equivalent resistance here. First, it would be very, very difficult. Secondly, you got two different batteries that are facing opposite ways. This guy's trying to make the current flow around like here, counterclockwise. This guy's trying to make the current, or I said that backwards. This guy's here, he's trying to make the current flow clockwise. He's trying to make it flow counterclockwise. You got fighting batteries here. You don't want to try to do some kind of equivalent resistance. It's not going to be your friend. So this is not a tool you want to use all the time, only in specific situations. So let's say we had, oh, maybe here's our battery. And like we could actually solve the entire circuit if I wanted. Say it's a 12-volt battery. I've got a 1 ohm, another 1 ohm, a couple of 2 ohms, and maybe a 3 ohm resistor. We want to find the equivalent resistance and find the current through the battery. So we're not going to solve the entire circuit, but we are going to figure out how much current flows through this battery. So the way we want to do this is kind of start out and work our way in. You might look at this and go, oh, look right here. That guy, and that guy are in series. No, they're not. Current that flows through here, right there at that junction, is going to split up. Everything that flows through these two does not have to flow through him. These two are not in series. These two are in parallel though. These two are in series. I could squish those two together if I wanted to. These two are in parallel. So the way I would approach this, squish these together, make these one equivalent resistor, then we'd have a bunch in series that we can add together. So we want to take this one step at a time and redraw the picture each time. So I've got my battery here. Remember, the big side is the positive side. That's where the current flows out of. I'm going to squish these two together into an equivalent resistance. Using that equivalent resistance will be 1/2 plus 1/2 will be 1 over Req. So that'll be 1. Flipping that over, those two have the same resistance as having only one resistor that's a 1 ohm resistor. Having a bunch of resistors in parallel drops your total resistance. Your equivalent resistance is always going to be smaller than any of your individual resistors. Now, from this picture, I've got a whole bunch of guys in series. Every charge that flows through him has to flow through him, has to flow through him, and so forth. These are all in series. So I could pretend that I only have one resistor. I'm going to squish all those together. We'll call it, I don't know, REQ2. Just by adding them all together. I got 1, 2, 3, 4, 5, 6. And that was a 12-volt battery. So the current that would flow around this loop, V equals IR, we could see pretty clearly there, that would be 2 amps. So I have a 2 amp current flowing out of here. So 2 amps flows through him and through him, but that current gets split up. And like, I'll tell you what the answer would be. If we were to use Kirchhoff's rules, we would get 1 amp flowing here and another amp flowing here. That 2 got split up. Those recombined back together to give us 2 amps back down here. Okay, let's do like a really nasty equivalent resistance problem. So let's say we got a battery. Okay, oh my handwriting's kind of bad here. Okay, we can only add things together that are completely 100% in series or completely 100% in parallel. Like, I don't know, like looking at that guy and that guy, they are not in series, they are not in parallel. In fact, just like as a general guideline, you kind of want to start further out and kind of squish the circuit down is like a guideline I would go for. Like these two right here, that 3 and that 4 are not in parallel because there's stuff that flows through the 3 that also has to flow through this other 3. So the way I would approach this is these two are in series right there, squish those together. Similarly, these two are in series. I could squish those together. Then I would have 4 parallels that I could squish together. Then I would have two in series. So let's approach it that way. I'm going to squish those together. So redraw it at each step. People that redraw these on each step tend to get them right. So that I could just do, right? That's 6 ohms, that's 4 ohms. Okay, now I'm going to squish all 4 of these together. Into one equivalent resistance. So that those are all 4 in parallel. That should be 1/4. 1 over REQ would be 1/4 plus 1/6 plus another 4th plus a 5th. Now, when I took this class, we didn't have the fancy calculators. I think I did have a TI at the time. Yeah, I'm sure I did, but it wasn't as fancy as yours is. I had to literally go through the math, find the common denominator, add all the fractions together, get an answer, flip it. You got a fancy calculator. It'll do all this for you. So I could literally just do 1/4 plus 6 plus another 4th plus a 5th. Get some nasty decimal. And then we got this 1 over button right there that will take the reciprocal of that. And we get this nasty decimal. And that's fine. For this class, I don't care. That's perfectly fine. You could just call that 1.15 and approximate the answer. That's good enough. But if you do want it as a fraction, right here, this math button, number 1 into fraction, 15 over 13. There's our equivalent resistance. What did I say? 15 over 13. So that's this guy here, 15 over 13. Now these two are in series, so I could redraw this circuit to be just one single resistor. That's 1 plus 15 over 13. So that would be what, 28 over 13 ohms. Okay, so these take a little bit of practice. Just practice them, do a few of them. They're not that bad.